Hello and welcome to my video lab report for Lab 2. In this lab, I observed the motion of an object that is dropped from rest and falls somewhat slowly straight down. I captured a video of the motion and analyzed the video on tracker to exact the object's position and corresponding time. Then I constructed a computational model based on the physics principles of Newton's second law or the momentum principle that only included the effects of gravity. Thirdly, I constructed a computational model based on physics principles, Newton's second law, or the momentum principle that included both the effects of gravity and the effects of drag. Then I compared my models to my observations by plotting graphs. So for tracker, I dropped a volleyball and the mass of the volleyball was 0.28 kilograms. Diameter of the volleyball was 0.2 meters, and I used tracker to measure the position over time. So here is my volleyball falling down video. Had my roommate help me out. She did a great job dropping it. As you can see, the ball falls down and I measured the position over time using tracker, and I got that data to do my comparisons. And then I analyzed the video. And then Newton's second law and the momentum principle are, so for Newton's second law is force equals mass times acceleration. And the momentum principle is that's momentum is equal to mass times velocity. So with these laws, I was able to come up with some formulas to add into my computational models. So first, for the one only with gravity, I used Newton's second law, which is this mass times gravity up here. And the only force acting on it was gravity. So the F net only equals W, which is the variable I used. And then for the computational model with drag, I have the similar W variable, except you have to add in the force of drag, which is B is a variable that I calculated later, I'll explain, and then the magnitude of the velocity squared, which is the momentum principle, mass times velocity. So this B variable vector I found to be 0.044. And how I calculated that is I basically just plugged in a bunch of different numbers to try to get the ending position of the computational model to match the ending position of the observed model. And I'll show you my code. Whoop, here it is. So this is my program. So right now I have it taking into account both gravity and drag. So when you run the program, you see this orange arrow is gravity and the blue arrow is drag. But if you want it to run without taking into account drag, just change that to 0. And here is just taking into account gravity. And then I took the data from these two models and my observable thing on tracker, and I made graphs. Look at them, they're beautiful. So this blue line here is what I measured on tracker. This yellow line is calculated with drag, and the red line is calculated without drag. As you can see over on the far right-hand side, there is a big difference between the model predicting only gravity versus the one that used drag in the calculations. That's because I made sure the drag B variable would allow the end of this line to match up with the end of the measured line. And what does it mean? Examine the velocity versus time predicted by your models with and without drag. Which models, if any, predicted terminal velocity? And so terminal velocity happens when the force of drag pointing up is exactly balanced to the force of gravity pointing down. What does this mean for the net force? Well, none of my models predicted terminal velocity because the force of gravity was much larger than the force of drag, which you could see on here when I put this back in here. What was it, 0.044? I think that was right. See how small the little blue arrow is compared to the big orange arrow? They're not close to being the same. But the net force at terminal velocity would be 0 because the force of drag and the force of gravity cancel each other out. And it's kind of like an object in motion stays in motion, so it's still moving even though the net force is 0. Next up, what if, imagine the object was initially thrown downwards, would the terminal velocity in this case be the same or different for the case where the object's initial velocity was dropped from rest? Justify your answer using computational models. An example of velocity over time. So if the ball's initial velocity is, oh wait 1 second, I got this. Okay, the first model right here, this is showing what it looks like when there's no initial velocity, where here I put in a negative 15 initial velocity, and as you can see, the blue arrow representing drag is much higher, and this means that the drag force will become higher, and the ball will reach terminal velocity faster, and the terminal velocity will be higher if you throw the ball versus if you don't throw the ball. The end. Thank you so much for watching my beautiful lab report, and I hope you guys have a great semester.